Hello everyone, this is our final review video. I'm going to just take our final exam review, the longer packet that you all received in class, and I've selected a selection of problems. I'm going to talk through them to help guide you as you prepare for our final. So look, I'm going to start with numbers 8 and 10 right at the top of the first page. So here they are asking us to describe the transformations to our parent function. So what I need to account for is what is this plus 6 and what does this minus 2 do? Well, that plus 6 moves our graph left 6 units, and that minus 2 moves our graph down 2. Remember, inside the operation, it's always going to be a horizontal move or reflection or stretch, and anything outside of the operation, outside of any grouping indicators like parentheses or a square root, that is going to move us up and down. Let's go the other way here. Here they are, number 10, they are giving us the description of transformations being applied. So we are going to take f of x, which is x squared, and transform it into g of x, our transformed function. So again, I have 3 different transformations here. Reflect across the x-axis, that's going to be a negative sign outside the parentheses. Then we have a vertical stretch by a factor of 10, and again, because it's vertical, that's going to be outside the parentheses. And then we need to account for one last thing, and that will be translating right, I want to change that color, translating right 8 units. And what that's going to do is going to be a minus 8 inside our parentheses, and we are all set. I'm going to keep things moving here. I'm going to jump down to number 18. Here they ask us to write a quadratic function in standard form with zeros of 6 and negative 8. Basically, they are giving us the answers to a quadratic, and they want us to find the quadratic that has those answers. So we turn these answers into factors. And you'll notice in factored form, the signs flip. And then to get out of factored form, we are going to distribute and use our FOIL technique. And we will end up with a real life quadratic in standard form, x squared plus 2x minus 48. So let's keep it moving here. I'm going to jump down on the next page to number 26. Find the zeros on a problem like this. We want to set our equation equal to 0. And if I am able to, I want to factor here. But there are not numbers that add to 6 and multiply to 18. So we need to use a different method. What I want to demonstrate is the complete the square method. So I'm going to move that 18 to the other side. Now I'm going to complete the square. I'm going to take this 6, I'm going to cut it in half and square that value. So 6 divided by 2 is 3. 3 squared is 9. I need to add that 9 to both sides of the equation, or else I have unbalanced what was previously balanced. So when I simplify here, I'm going to have negative 9 equals x plus 3 quantity squared. When we solve this, we're going to take the square root of both sides. So x plus 3 will equal plus or minus 3i, and x will equal negative 3 plus or minus 3i. So that is how we would approach this. That is completing the square. We could also use the quadratic formula. I'll demonstrate that down on number 28. Complex conjugate, this is a very quick question. This is really a vocab word about what is the complex conjugate. All we need to do is switch the sign in the middle of that complex number. The complex conjugate of 3 plus 4i is 3 minus 4i. Finally, on number 28 here, I have a quadratic. Again, I'm looking for the zeros or the solutions, and I have unuseful values as far as factoring goes. So I'm going to use the quadratic formula here. I would prefer the quadratic formula here over completing the square because our b value, our linear term, is odd. Cutting that in half will give us a fraction, and I know all you people don't really like fractions, so I will avoid that whenever I can. So I'm going to solve this using the quadratic formula. the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. This is a formula you will have on your formula sheet for the final. And this would be our final answer. -7 plus or minus root 13 over 2. If square root of 13 was simplifiable, we should do that. But in this case, 13's prime. There's not much we can do with it. All right, let's keep it moving here. We are going to jump down. There's a section of problems here on imaginary numbers. And as we worked today, I definitely got the sense that we could use some help. So on this first one, pay attention to our signs here. We are subtracting. And when we are adding or subtracting imaginary numbers, we are going to just combine like terms. So 5 minus 6 is -1. -2i minus 8i is -10i. And we are done. 41, we are now multiplying. So we are again going to treat I mostly like a variable. We're going to distribute and get 24i minus 36i squared. So I say usually we treat I like a variable. Once I has an exponent, like 2, things get different. So I squared is the same as -1. So we're going to plug that in, and we're going to rewrite this answer as positive 36 plus 24i. Notice we always like to write complex numbers with the real part first and then the imaginary part second. I'm just going to work over to the side here for number 42. They are asking us to simplify -8 times I to the 20th. I to the 20th is one of 4 options, right? Remember we had I to the first, that was I to the second was -1, I to the third was -I, and I to the fourth was 1. And then I to the fifth would go back up and we would continue the pattern, right? So we need to figure out basically which of these 4 options does I to the 20th represent. Well, 20 is divisible by 4. So it would fit in to our final spot here. This is just going to be -8 times 1, which we know is -8. Finally, here we're going to use that a complex conjugate we saw earlier. So when we simplify these fractions, we multiply the numerator and denominator by the complex conjugate of the denominator. What you can see here is that we have an imaginary number in the denominator, which is a square root, so we have to get rid of it. So I'm going to simplify this. I always work on the denominator first. It just tends to simplify quicker. And in this case, I'm going to have 25 minus 9i squared. And then in the numerator, I'm going to have -10 plus 6i plus 10i, so that's 16i, minus 6i squared. I'm going to keep simplifying. I squared is -1, so we can't do much with it. So that's going to, we can't do anything other than turn it into +6. So we will have -4 plus 16i in the numerator. And then in the denominator, we will get 34. 34 is 25 plus 9. -9i squared is the same as +9. All right, so that's our section on imaginary numbers. I'm going to keep moving here. Please feel free, if I sped through anything, just to rewind and try again. I just wanted to refresh your memory on correlation and correlation coefficients. So this section, 64 through 67 on your packet, has a few different correlations. So correlation, we care about 2 things. We care about the direction, and we can use the sign of the slope, S-I-G-N, not S-I-N-E. And this has a positive slope, so this would be a positive direction correlation. And because these points are pretty closely bunched together, I would also say that this is a strong, so a positive and strong correlation. Why is it positive? The slope of the line of best fit is positive. What makes it strong? Our points are pretty close to that approximated line of best fit. 65, we're going to see something similar. Again, those points are really close to that line, so this is still going to be strong. But what you notice here is that the slope is negative, so this is going to be a strong negative correlation. The way we quantify those correlation coefficients, those correlation relationships is through something called a correlation coefficient. The correlation coefficient is R, and R exists between -1 and +1. The closer it is to 1 or to -1, the stronger the relationship. So in number 66, we have a positive slope. So our R value is going to be positive. And I would say this one's pretty close to 1. I would approximate this to be about 0.9 or 0.9, somewhere between 0.9 and 0.95. Right, it's positive because we have a positive slope, and it's pretty close to 1 because those points are pretty tightly packed. On number 67, again, we're going to have that similar relationship. Oh, sorry about that. Some sort of best fit like that. We definitely are going to have a negative slope. This one, I think, is still strong. Again, I'm going to say somewhere between -0.9 and -0.95 as an approximation of these values. All right, we're going to keep pushing here. I know there's a lot to wade through. So I'm going to jump down to number 80. And I want to talk through something that I think we didn't quite wrap our head around the first time. So the discriminant is a term you may not recognize, but the discriminant is this stuff here. The discriminant is the stuff under the radical in the quadratic formula, b squared minus 4ac. So if we take their discriminant, -2 squared is 4, minus 4 times 1 times 1, we get 0. So now we need to interpret that answer of a discriminant of 0. If our discriminant were, positive, we would have 2 real solutions. If my discriminant was negative, I would have 2 imaginary solutions. And if I have if my discriminant equals 0, this case, the situation that we have with a discriminant of 0, we will have 1 real solution. This is a situation where the vertex of our quadratic is on the x-axis. All right, and then right below this, we had a projectile motion problem. We are given an equation, -16t squared plus 20t plus 6, and we want to figure out that path of the ball. When does that ball reach a height of 10? Right, that's what they're saying. The hoop is 10 feet high. How long is the ball in the air before it goes through the hoop? So we're going to set this equation equal to 0, as we always do when solving. And then I'm going to factor out a -4 to make my numbers a little bit easier to work with. Oh, sorry. If I factor out a negative, I have to switch all 3 signs. Plus 1. So that's going to make our factoring quite a bit easier. So when we factor this fully, we're going to get 4t as one of our factors. And it's got to be -1, -1, and this will work. What this means is that the ball in this particular problem is at a height of 10 at 2 different times, at 1/4 of a second and 1 second. That 1 second is going to be our better answer. That 1/4 of a second is basically the ball hitting 10 feet on the way up just after the player shot the ball. All right, and then we're going to jump all the way down to 99. We're getting close to the end here, team. We got about 4 or 5 more minutes. All right, so here, if the behavior of a function is down on the left and down on the right, what do you know about the degree and the coefficients of our polynomial? So I need to figure out what I know about the degree and what I know about the leading coefficient. So what we know here is that we have some graph. We don't necessarily know what it does in the middle, but we do know that the arrows are both pointing down. So we want to think about the type of functions that we've seen this year where both end behaviors point down. I'm thinking of like negative x squared is a parabola that would meet that description. Its degree must be even. And if it opens down as opposed to up, the leading coefficient is negative. All right, let's move on to the Q2 portion of this. We have a few log problems that I wanted to refresh your memory on. You know what? I feel like I skipped something that I wanted to see. Likely not. Sorry, everybody. All right, let's look at some logs here. So here we have log base 9 of 27 plus log base 9 of 3. And before I go any further, I think I want to condense these logs. This is something that we spent a little bit of time with. I have logs that have a similar base, so I can rewrite this as a as a single base. When we add exponents, that happens when we are multiplying bases. So we can take two logarithms being added together and write them as a single logarithm where the argument is being multiplied. And if we were to simplify this, we would have log base 9 of 81, which is going to be 2. Let's look at another one. Here, this is a common thing you'll be asked to do. Rewrite as a single logarithm. I usually just start right there and write log and open up a nice tall set of parentheses and fill in some details from there. So I'm going to go term by term here. Remember that when we have a coefficient like this, it can become an exponent. So that's going to be 3 squared in the numerator times 2 to the third. And then we have a negative. What that negative is going to do is it's going to move our last piece here into the denominator. So this log of 6 is negative, so this is just going to move into that single log in the denominator. So now I'm going to simplify what I have inside the fraction. I'm going to have log of 9 times 8, which is 72 over 6, and we will get log of 12. That is as far as we can go. Another one, this is similar to a problem you saw on your most recent test and one that we could use some improvement on. This is a situation where we really need to recognize that the log base and the exponent base are the same. And that's a little bit trickier in this situation because both are log base 10. And even though they don't write it, we assume it to be there. So, all right, let's look at each of these individually. What this first one is asking us to do is to find, it's really asking us 10 to what power equals 10 to the 9th. Well, this first term here is just 9, right? This 9 can come and hang out by itself. Over here on the right, that exponent is a value, it's some number, and when I raise 10 to that number, I get 5 as a result, right? That's just the exponent I'm talking about. When I raise when I raise 10 to this number, whatever this exponent is, log base 10 of 5, I get 5 as a result. Well, now I'm going to take 10 and raise it to that exponent. So I'm going to get 5 as a result, and my answer here is 14. All right, let's see what else we got here. Some rationals. That's what I thought I skipped earlier. Come on, Waz. All right, let's take a look. So we're going to simplify some rationals here. And then they also tell us to state any domain restrictions. We'll talk about that briefly. So when we simplify, this is a fancy way of saying factor and cancel if you have a rational. So let's factor it. On the numerator, we're going to get x minus 5 times x plus 3. In the denominator, we're going to get x minus 5 times x plus 1. It is only at this step when we have factored both the numerator and denominator that we can cancel. So our simplified form would be x plus 3 over x plus 1. But remember with rationals, we always want to state what x cannot equal. X cannot equal -1 or 5. If we plugged 5 in over here, the denominator is 0, and we're in trouble. Let's look at one more here. This is kind of a silly looking one once we start factoring it. But what I'm going to do is just to demonstrate that we're really doing the same thing when we cancel a simpler fraction. 9 is the same as 3 times 3, and 3 can come out of 15a as well as negative 18. I split those 3's on the top because it's easy to see which one gets canceled, and we could simplify this to 3 over 5a minus 6. In this case, a cannot equal 6 over 5. And the way to do that is just to set the denominator equal to 0 and solve for your variable. All right, we have just 2 more that we're going to finish up with here, just a couple more rational problems, and we'll call it a day. So on this one, we are dividing, and what I want to keep in mind here is keep, switch, flip. That is how we divide. So our first terms here, n plus 3 over n plus 2, they're going to be unchanged. And then we're going to switch this to a multiplication problem and flip our second fraction here. So n minus 1 squared is n minus 1 times n minus 1. And then I'm going to factor that numerator and put the result in the denominator. Then we get to the fun part. Now we can start hacking and slashing, cancel anything that we see in both the numerator and denominator. In this case, our simplified form will be n minus 1 over n plus 2. All right, one more problem here. I want to refresh solving rationals. So what we want to do here, we want to remember that we all hate fractions, right? And we want to lean into that distaste for fractions. We are going to get rid of them. So we are going to multiply by the least common multiple of our denominators. In this case, 4x. When we multiply that first term times 4x, the 4's will cancel, but the x's will not. We'll have 15x. In our second term, that 6 over x term, the x's will cancel, but the 4 will not, so 6 times 4 gets us 24. And then over on the right with our term 3, nothing's going to cancel, so we'll have 12x. Now I have an equation that I can solve. So I'm going to subtract 12x from both sides, and then divide by 3. Oh, excuse me. And get my answer. The only thing I want to remember, I want to make sure I check my answer. If I plug this into my original problem, I have no denominators that equal 0. So this is a legitimate answer, and we are done. If there are any other problems that you'd like to see, please reach out either via email or through any other channel, and we can go and get that done. Thanks, everybody, for your time.